And welcome everyone to another riveting episode of the development and analysis of human movement. And today we are going to go over the exciting world of the hand and the wrist. Alright, so let's get started. So we have the hand and the wrist here. So let's go ahead and begin. Our objectives are going to be, we're going to have an overview of the general anatomy of the hand and the wrist. We're going to describe the normal alignment of the hand and the wrist. And we're going to just have a great time learning about the hand and the wrist today. So the wrist joint is a complex joint, or the wrist is a complex anatomical feature on our bodies because it allows us to do many things that we wouldn't be able to do without it. It really has three main joints that we look at. We call the radiocarpal joint, the midcarpal, and the carpometacarpal joints. So if we look over here, the radiocarpal joint, that's right here, right? Radio, radius, carpal, the carpals, okay? Now the ulna really doesn't play a huge part in this joint because the scaphoid is the main player in this game, and that's this guy right here. We'll go over the names of those later, but it's really the scaphoid and the radius that make the most contact throughout this joint. The articulation of the radius on the scaphoid, lunate, and triquetrium is what really constitutes this joint. The ulna is not part of the joint because of the articular disc between the triquetrium and the ulna. So you see there's a lot of space because that ulna is a little shorter. So it's filled with a fibrous disc to help that as well. And the pisiform does not articulate with the disc, thus it eliminates it from the inclusion of this joint. And that's this little guy right here, the little pisiform. This is a synovial joint, so it's wrapped in a capsule and it secretes synovial fluid, and it has a vacuum pressure seal that kind of helps keep that joint stable. It's biaxial, so you have two axes of rotation with it. You have flexion and extension, which happen in the sagittal plane, and you have a radial and ulnar deviation, which happens in the coronal plane. Then we move on up and we have the midcarpal joint. So just as it sounds, it's the middle of the carpals, and it's where they all articulate within each other here. The articulation of the top row and the bottom row of these carpal bones is what constitutes this joint, and the transverse arch is present, and that allows our carpal tunnel to actually occur within this joint as well. So the carpometacarpal joint is the end here, and this is between the carpals and the metacarpals, which are the long bones in our hand. The articulation between these is what makes that joint up, and you can see here in neutral, where our hand is straight, that's what happens. And then we have extension when you move it back, and flexion when you move it forward. Move my camera here. There we go. And then we have ulnar deviation, where you bring the hand over towards the ulna, so like that little rotational movement. And then we have radial deviation here. Sometimes they call that, instead of deviation, they call that flexion, so radial and ulnar flexion. Bones. There's two rows of 4 bones. So in our proximal row, we have the scaphoid, the lunate, the triquetrium, and the pisiform. Then in the second row, we have the we have the trapezium, the trapezoid, the capitate, and the hamate. What's big is that, like I mentioned earlier, the scaphoid supports most of this weight in the wrist when the hand is fixed. So like when you're pressing up against something, it's mainly that radius and that scaphoid that really make a lot of that contact. And that's why this bone's actually most often broken as well when you look at wrist fractures or falling on an outstretched hand. And that's because this little scaphoid has to absorb so much force of all your body weight falling on it from the hand, and then transfer that to the radius as well. And then the bones are small with concave surfaces on the anterior and convex on the posterior. And then a good way to remember this is some lovers try positions that they can't handle. That's the one I always remembered when I was in college, so I'm passing along that generational knowledge to you guys. Okay, Sum is the scaphoid, Lovers is lunate, Tri is triquetrum. Positions is pisiform. That is trapezoid. That is trapezium. They is trapezoid. Cant is capitate, and handle is the hamate. So some lovers try positions that they can't handle equals those. So a good way to remember those, because that'll probably be on your quiz. Wink, wink, nudge, nudge. So then let's move on to the types of joint in the hands and the wrist. So if we're going to go ahead and look at the bones that are involved, let's look at the joints as well. So we have a plane joint, which is a gliding non-axial joint. So it doesn't really have any planes of motion. This is really what happens with the carpal bones. The carpal bones are the long bones in the hand, and they just kind of glide over each other when we go into flexion and extension, or ulnar or radial deviation. We also have hinge joints, which are uniaxial, and those are the interphalangeal joints. So between our fingers, right here. They produce flexion and extension. Pivot joints, which are uniaxial, so they do superior and inferior, or they do pronation and supination, and they are located in the superior and inferior radial ulnar joints. Okay, they just kind of pivot on each other. Then we have the condylar, which are uniaxial, so one plane, and metacarpals and the interphalangeal joints are these, and they do flexion and extension. You have an ellipsoid, which is a biaxial, and that's like the radiocarpal joints or the metacarpal phalangeal joints. Those do flexion and extension, abduction and adduction. And then we have saddle joints, which are biaxial as well, and this is really only in our thumb, in the carpal metacarpal joint of that thumb. And they do flexion and extension, AD and abduction. And there's actually a little bit of rotation that also happens when we have these types of joints. So let's zoom in over here and we can look. And you see, it shows here a condyloid joint, right? So a condylar joint is like our metacarpals and our interphalangeal joints, flexion and extension. So you can see that it's got a wide base, right? And it rotates on another. Convex on concave, just like this little ball that rolls in this groove kind of, is what it's kind of giving you an analogy of. And that's what we have when we have the metacarpals bending and flexing and extending. Then we have a ball and socket, which is like our shoulder, which we've already discussed, that ball rotating on the T on the glenoid there. The hinge joint is a great example of also some of our fingers as well, but also the interphalangeal joint, so between our phalanges. And that is also in the elbow with the humerus and the ulna, and it's a hinge, so it just bends and flexes and extends. Okay, so it's like a convex groove on a concave groove as well. So our pivot joint is uniaxial and superior and inferior radial ulnar joints. So the radius and the ulna, as they at the top and bottom, if you remember how they have that groove, right? And that's just a pivot. It's just a little rotation. It's not a lot to call it a rotational joint, but it's just a little pivot. Okay, it just shifts around there. Plane joints are here, and it kind of shows you what those are. Two flat surfaces just gliding across each other is what a plane joint is. A saddle joint is where you have two concave surfaces sitting over each other that allows them different planes of motion. So it gives you that AD and abduction, and it also gives you that flexion and extension. And you can see how you could get a little bit of rotation with that as well, but eventually the bones would touch each other and stop each other from doing that. And then you have this ellipsoidal, which kind of also is very similar to a saddle, but it's more of that concave convex, and it just kind of sits and rolls within that. So if you put a golf ball on a tee and kind of rolled it around, that would be more your ellipsoidal, whereas that the ball and socket has a vacuum seal that kind of sticks in there. The ellipsoid doesn't actually sit and suck inside that joint. It just kind of sits on the top. So then when we look at the wrist, we have to realize that, okay, we have all these little bones, right, that are kind of connected in here. How do we actually support those other than muscles, right? So we're going to need some ligaments in there. So the main ligaments, because there's a lot of ligaments in here as we look at our 3D model man, you'll see how many there are and what it looks like. And it's a synovial joint, like we said, so there is a little capsule in there. So we're just going over 4, and these 4 don't make up the entire capsule, but it's the main ones. So we have the radiocollateral ligament. So since it's a collateral, we know it's on the outside, and it's going to provide some type of lateral support, collateral, so the outside. So that means it's a co as well, so that means there's another one, the ulnar collateral ligament, right? The radiocollateral ligament provides that lateral support attaching to the styloid process of the radius and the scaphoid and trapezium, trapezium. Then on the ulnar side, we have medial support attaching to the styloid process of the ulna and the pisiform and triquetrum. Okay. Then we have the palmar radiocarpal ligament, and that attaches from the anterior distal radius and the ulna to the proximal carpal bones and the capitate. It's a thick, broad band, and it's taut when we push our arm back. So it really provides that anterior support from keeping all these bones just falling out of our wrist. And then we have the dorsal radiocarpal ligament, which attaches on the posterior aspect of our radius and the posterior distal scaphoid lunae and triquetrum, and it's taut in flexion, so it keeps them from popping out the top of our wrist as well. The joint capsule encapsulates that radiocarpal joint completely, and there's an articular disc that closes the gap between the ulna and triquetrum, which we've already talked about, and the lunate. What's next? Muscles. So before we dive into the muscles, let's take a look at some of that bony anatomy with our model man here. Okay. So you see this kind of right palmar aponeurosis here, and that's just kind of a thick band of tissue that goes across of our muscles as well. Turn that off. Let's hide that. Let's hide all these nerves, and you can see all these nerves, all these muscles that are happening here. Let me pause it while I clean all this up so you guys aren't wasting your time. So we're back, right? And we can see now really how that wrist is really taped together. So look at that palmar aspect on the palm side of our hand, right? Look how many ligaments cross that. You can't even really see all the bones of the hand there, of the wrist, I mean. But on the back side, it's a little bit easier to see those. You have many more smaller ligaments that really make that up, right? So you have our intercarpal joint ligaments right there. Here's our radiocarpal here. Joint ligaments kind of helping support that laterally. This is a dorsal radiocarpal ligament right there. Let's see if I can click here, because this one is our, I should have had it, the ulnar carpal ligament right there. The UCL, right? And you can see how we really focus on just a couple of these bands, but you see how there's multiple of them. And even the people who named them just said, let's just throw them all together into the ulnar carpal ligaments. And then here's our radiocarpal ligaments here that help those. And you can see how all these kind of form a little capsule as well. Here's a retinaculum here that kind of helps keep all these flexor tendons down when I actually put the muscles back on. You'll see that this retinaculum actually holds all that down. And you see how there's a tunnel there. So you can see how it holds all the fun stuff down and creates space to hold that. And then you can see here all this space between the ulna. Look at all that space, right? A lot of space there. But then when we look at our scaphoid and our radius, it's quite articulate, right? You see there's a lot of contact space there, and you can see how that scaphoid there, and then we get rid of our lunate so we can, or not our lunate, we want to get to that. And the lunate have that articulation there. You see how they're so close to the radius? And then right here, the triquetral doesn't really have much at all. And that's where that fibrous disc comes in handy. So as we look at that radiocarpal joint, that's why it's mostly those two. And that's why it's mostly that this guy is fractured, right? because of that. And you can get this lunate fracture as well, which is bad because it's got bad blood supply. So it doesn't heal very well as well also. Okay. So let's look at our muscles. We have the flexor carpi ulnaris. That is the medial epicondyle, and it goes to the pisiform, the base of the fifth. And the wrist flexion and ulnar deviation is what it does. It's very superficial, and it can assist with elbow flexion. So you look at this here, and you see it does cross that joint, that elbow joint, so it can assist a little bit with that, especially since most of that muscle belly is closest to the elbow there. Right, so it does create a lot of force at that elbow to help that out. Then we have the flexor carpi radialis, and that does originates at the I can't speak. That originates at the medial epicondyle as well, and it goes to the base of the second and third metacarpals, and it produces wrist flexion and radial deviation. It's superficial, and because it does cross the elbow joint, you have to remember that it can also assist with wrist flexion. Okay. Palmaris longus, that is on the medial epicondyle, and it goes to the palmar aponeurosis. It assists in wrist flexion. It's superficial, and it's actually missing in about 21% of the people, or the population. It is found with the first and fifth phalangeal opposition and slight wrist flexion, so it does here. Okay, you can see it. Let me try and get it here. As I bring my fingers here and flex, okay? So you'll see it in the middle of my wrist. It'll pop. Guess you can't, it's right here. You can kind of see it. Let me see if I can get the lighting a little better. Can't really see it, I give up. But we'll do it in lab and you guys can see and see how that pops. And some people, it might not pop, and that means you don't have one. A lot of times that's actually, this tendon is what they'll take, and they actually use it to repair the UCL in the elbow if you have Tommy John surgery. Since 21% of the population does not have it, they use it and they say it's not really that, it doesn't create enough force that it's an issue. So they take it out and provide more medial support to that elbow as well. Okay. Extensor carpi radialis longus originates at the supracondylar ridge and it inserts on the base of the second metacarpal. So you see it right here. Okay. It provides wrist extension and radial deviation. So we know it's on the lateral aspect of that elbow because it does wrist extension. And remember those rules I showed in the last elbows video, where any muscles that originate on the outside of the elbow really help with extension, and the medial work on flexion. It passes under two tendons for the thumb and the extensor retinaculum as well. So right there. So sometimes you can get some thumb issues if this guy gets a little tighter and inflamed. The extensor carpi radialis brevis, it originates at the lateral epicondyle, and it inserts on the base of the third metacarpal, and it assists with joint or wrist extension. It passes under two tendons that go to the thumb and under the extensor retinaculum as well. It has a short movement arm, and it leads to only a minimal assistance in radial deviation because that movement arm is very short. Extensor carpi ulnaris, it originates at the lateral epicondyle as well. It goes to the fifth metacarpal right here, and it does wrist extension and ulnar deviation. So you can see how it would pull that wrist back and over towards our ulna and create ulnar deviation for us. Here's a little cheat code for you. You take the opposite hand of your palm, take the thenar eminence, so this fatty piece here, and you're going to go over your medial epicondyle. So like, yay. Then as you, hang on. Let me transition here. You can see better. So if you do here, so you take your arm out, spilled my coffee. Take it here and lay it across like that is what we're talking about here, okay? So you see, boom. Let me see if I can get higher up. So you lay it across just like this, okay? And what that does is that actually, let me transition back for you guys. it lets you kind of see where those muscles are going to lie. So that thumb is where that pronator teres would be. The index finger would be your flexor carpi ulnaris or radialis. Your middle finger would be your palmaris longus if you have it, and your ring finger would be your flexor carpi ulnaris. So you can see here the giant arm man here. You can see here the flexor carpi radialis comes along there, the palmaris longus there, flexor carpi ulnaris there, and our flexor retinaculum. And then on the back you see the extensors there as well. So let's go and look at that in real life here. Let's reset it. Boom. Let me get rid of all these nerves real quick. I'll be right back. Alrighty, I'm back. So now you can really see the entire arm here. And this is the posterior lateral aspect of our arm. So let me rotate it here so we can get a good picture. Okay. Now you can really start seeing, here's our right extensor digitorum, how it runs all the way down into those fingers. Down into here. You see how it's highlighted. And see how it goes all the way to the tips. Anything yellow, you see how it goes to the tips. Now you notice how it doesn't actually get the thumb as well though, right? Because we have another muscle for that. I want to make sure I don't delete anything. Here's our extensor digiti minimi. So that's just the pinky. Okay. And I don't have all these listed in the PowerPoint. Only the ones in the PowerPoint are the ones I actually want you to know. Okay. The right extensor carpi ulnaris. So it's a shorter muscle, right? It doesn't actually go all the way down to the tips like the other ones do. It stops right there at the base of that fifth. Here. Okay, now we move over to the thumb side and we see our pollicis muscles here. Our pollicis longus. You see how that goes to the thumb all the way to the tip. And then we have the pollicis brevis. You can just remember them as the pollicis group. It's not a big deal. And then the pollicis longus goes all the way down as well, all the way to that tip. Okay. And then this long tendon here is the right extensor carpi radialis brevis. You can see how it kind of comes across down underneath all this musculature here, all these tendons, into that third. And then as we come across more, the extensor carpi radialis longus, and it comes across all the way to the first, or the second, I'm sorry. The first is our thumb. So our index finger. Now we're looking at that brachioradialis, the big workhorse, right, of our elbow. Let me pan a little bit better here. And you can see how that guy comes all the way across that elbow into our wrist and really is the big workhorse of a lot of that flexion. We have the pronator teres, little guy that sits up top. We have that, this would be where that thumb, right? So on that thumb trick I just showed you, that's the pronator teres right there if you lay your arm across. Here's our flexor carpi radialis. Here is our palmaris longus right here. Here is our flexor digitorum superficialis. Just know the flexor digitorum, the profundus, and ulnaris again coming across. Okay. So now you can really see, and this is that anconius here that we talked about in the elbow. So you can kind of see how that works. Now you can see that retinaculum now on me that I showed you before. And you see how its job now, how that tunnel closed up completely almost, because it's so full of just tendons and ligaments. Then you look here at the vascularity and the nerves, so you know how innervated this hand is, so that you know exactly how much pressure you're using, how much force you need, and why it hurts so bad when you jam your finger in the car door, things like that, because you have all these nerves, so that, and why it bleeds so much. Look at all these blood vessels as well. So when you cut your finger or you slam it in the door, It's very highly innervated by nerves, and it's got a good blood supply, so that's why you also kind of cut your finger and it bleeds like no other, even though it doesn't really hurt or it's not even that deep. So let's look at our joint motions. In neutral position, that's when the wrist is in anatomical position in a straight line with the forearm. Flexion, we have 90 degrees of wrist flexion, and that's when the anatomical position, the fingers will move anterior towards the front to your forearm. Extension, we have about 70 degrees of wrist extension, like that, okay? And that is when the anatomical position, the fingers will move posterior. You have radial deviation, which is 25 degrees of radial deviation, so this way. Make sure they don't cheat by sliding the arm out. And then ulnar deviation the other way, 35 degrees of that. All the end fields are firm except radial deviation, which is a hard end field because the radial styloid process bangs against the scaphoid in that. The joint is convex on concave. Okay, so you can see here our concave and convex rule, how that shows how that moves, which way. Okay. Now the wrist is one of the best examples of a lever system, right? Because our body, all these joints are just levers. That's all it is. It's a third class lever, and it's a short force arm when it's unweighted. So when this is not weighted down, the force arm on that wrist is very short. So you see here, muscles come across, wrist flexors, they attach here, pull, right? Because it's such a short force over the joint, it has a lot of strength and power with that, which allows you to really create a lot of force, fast movements, right? Because all it's got to do is go against the gravity, which is a very short resistance arm as well. But as we look down here, let's say I'm grabbing a plate, I've now moved that gravity force from here out to the end along with the force of whatever I'm holding. So that's increased my resistance arm while not increasing my force arm, which causes a lot more force on that wrist joint. Okay. The hand. It's incorporated into 5 major joints. The carpometacarpal joint, the articulations of those. So this is in the hand part. So we talked about the wrist, now we're breaking it down into the hand. The carpometacarpal joint, which articulates, we have our first metacarpal articulates with the trapezium, the second metacarpal articulates with the trapezoid, the third metacarpal articulates with the capitate, and the fourth and fifth metacarpals articulate with the hamate. So that's this right here. Okay, that's what we're talking about. The joint structure, the first carpometacarpal joint is biaxial saddle joint, concave and convex. Okay. The second to fifth is non-axial, plane-shaped, irregular synovial joint. So they kind of glide across each other. If we remember what our plane-shaped joints do, you can see here it shows you in this picture 2 flat surfaces just gliding across. And here's that. Excuse me, that saddle joint on that thumb and how that moves. You can see it right there. Oh, excuse me. Opposition is when in anatomical position the pad of the first metacarpal is perpendicular to the palm, then the thumb is opposed to the pad and the pad is brought parallel to the palm. So we're looking at this motion right here. And rotation's not voluntary on that. So while you get a little bit of rotation with that, it's not voluntary. It's an accessory motion due to the inability of the individual to contract a muscle to cause that rotation. So when that thumb comes across, it's a byproduct. You have no way of actually doing that yourself. There's actually a good video of this, and the rotation occurs to accompany the active movement that is essential to normal movement. Let me just finish this slide and I'll show you guys. The first carpometacarpal joint is the most mobile, followed by the fifth carpometacarpal. That's why we do opposition. The second through the fourth is very limited with mobility. And the fifth carpometacarpal joint is a condyloid shape. So we're looking over here. And it allows for a small amount of opposition, and you place hand in your fist and your arm is supinated and the elbow is flexed, and you can note the motion as you move from the flexed fist to a relaxed fist. You can see that. So we can look at this hand grip here, and it shows the opposition pretty well. It's digitized, and it moves for us. Okay, so you can see, I'm gonna rotate. Uh-oh, okay, I thought it froze. At that joint there. Okay, this is what I'm looking for. Trying to pull it over, boom. Too much, okay? So you can see how it flexes and it adducts, right? So we get a little bit of adduction here as it moves over, and then it goes down. Okay, here we go again. Boom. And you see that little rotation that happens? That's not a voluntary movement. That is completely because of the fact that it happens. So you see here, goes opposition and then full flexion. So making the fist, and as we go here, you see how it does that. So flexion, and then a little bit of rotation happens there, and that's an accessory motion. You can see how it highlights what muscles are actually being flexed as we do each motion. So as it goes flexion, these highlight, and as we extend it, these highlight. And then you see the pollicis, muscle flexor pollicis happening, and then the extensor pollicis happening. Okay. Carpal metacarpal joint motions. We have flexion and extension. So just bring our thumb in and out. AB and AD. So here. And then we have opposition here and reposition. The metacarpal phalangeal joint, the MCP joint. So we're looking here. It's a hinge joint. It's unlike the carpal metacarpal joint or the metacarpal phalangeal joint of the first. It's not very mobile. It only allows flexion and extension. It's uniaxial, so it's concave and convex, and so it follows the concave-convex rule. The second and fifth metacarpal phalangeal joint is biaxial condyloid joint and concave based on convex metacarpal head, so kind of reverses it there. The interphalangeal joints right here, these are all the same, so I'm just kind of flying through this. You can read it or pause the video and read through if you want to read my notes there. And you can see second in the interphalangeal joints is, I don't really know what I'm saying there. So the proximal interphalangeal joint is the base of the middle phalanx to the head of the proximal phalanx. Distal interphalangeal joint is the base of the distal phalanx with the head of the middle, and uniaxial. So it's flexion and extension, and it's all concave on convex on these interphalangeals right there. Okay. Okay, that's what I was saying. I'm sorry. So this interphalangeal joint, you can see it's here. We only have one interphalangeal joint in the thumb because we only have 1, 2, 3 bones, right? But in the hand, or in 2 through 5, we have 1, 2, 3, 4 bones. So we have the distal interphalangeal joint and the proximal interphalangeal joint right there, whereas we just have an interphalangeal joint right here on the thumb. So that's what the 1 in the first, and then the 2 in the 2nd through 5. The arches of the hand. When we rest our hand, we have 3 distinct arches that are present. The longitudinal arch, and that begins at the wrist and runs the length of the phalanges. Okay, right there, right there. Then we have the distal carpal arch, which is formed by the metacarpal heads. And that's this guy here. And then we have the proximal carpal arch, which is formed by the proximal end of the metacarpals and the carpal bones. They all contribute to various gripping positions. And then the muscles, again here. The general roles, muscles across anterior do flexion, posterior extension. Pollicis means thumb, digitorum means fingers. And then extrinsic muscles are muscles that have a proximal attachment above the wrist joint, and they assist in the motion but are not the primary movers. So we have the extrinsic muscles. We have the flexor digitorum, the flexor superficialis, profundus, and longus. So you see them here. So flexor, digitorum, pollicis, fingers, thumb. extrinsic muscles, posterior, abductor pollicis, extensor pollicis, and extensor digitorum. So you see them all here. They're all in order, left to right. I'm kind of going quicker because I'm at about 35 minutes and I don't want to make this video drag on for you guys. The intrinsic muscles have proximal attachment at or the distal to the carpal bones, and they function to move the first through the fifth phalanx or the metacarpals. And many smaller muscles that flex, abduct, and adduct the hand extend the metacarpals and the phalanges. So you can see how a lot of these, especially these lumbricals, run between each little bone here. Grips. We have 3 different types of grips that we have. We have a power grip. Okay, that's our fist. When you just grab a hammer or a doorknob, it's typically an isometric contraction. So whatever you're grabbing is solid, or like a handle of a sledgehammer. It's solid. It's not going to give it in. It necessitates a large amount of force, and the flexors grip the object while the extensors stabilize the wrist in neutral. The thumb adducts and flexes. Then we have 3 other types. The cylindrical grip, the middle, where they're grabbing like a jar. A spherical grip, where all the fingers and the thumb are abducted around an object. And then we have a hook grip, which is the 2nd through the 5th fingers wrapped around an object in a hook-like manner. And the metacarpal phalangeal joint extends while the PIPs and DIPs flex. The proximal and distal phalangeal joints. Then we have our precision grips. Precision grips have 5 variations of these. These are our fine motor skills. They typically involve fine movement and accuracy, and the object is usually small and fragile. So you can see on our pictures to the left, we have a coin, a key, a pencil, a pen, or a plate. So our pincher grip, that involves the thumb and 1 finger, pad-to-pad grip. Then we have the pad-to-side, where you pinch it across the side of your thumb here, and the thumb presses against the object, and it's a strong grip, but it's less fine motor skills. The tripod grip, that's like our pencil grip. That's a thumb and the first 2 fingers. It's the most common precision grip that we use. We have a side-to-side grip, which is adduction of the middle finger and index finger, and it's weak and not very precise at all. And then the lumbrical grip, which is metacarpal phalangeal flexed, and the proximal and distal interphalangeals are extended, and it's often used when an object needs to be kept horizontal, like holding a plate. So that's the end of the PowerPoint. I think I just wanted to show one more thing really quick, if it's in here. We saw the hand grip. This is a distal radius fracture, tennis elbow. So if you guys aren't on this yet, check out the BioDigital, because it does show a lot of this. So you can see the carpal tunnel. I think that's the one I wanted, just to make sure I got the right one. Yeah, we're gonna go with that. So you can see, as I was talking about, that tunnel and the arches of the hand. I thought there was an arches of the hand one, but I guess not. But you can see how the arch happens here. The flexors and all those ligaments run underneath there, causing some pain in that median nerve. I know we talked about that. Let me look it up. Hand. We looked at that. Rheumatoid arthritis, fractures. Yeah, that's about it. I think that's good enough. All right, so be ready to go in lab. We'll learn some new stuff, play around with some palpations again, some ranges of motion, and we will take it from there. All right, everyone, have a good day and take care.